So chapter 12 and chapter 13, we're going to have 4 questions, maybe 2 questions for each chapter. And you're only allowed to use your equation sheet. As a study, I would recommend you study the notes, number 1, and then look at the homeworks problem and try to make sure that you solve problems on your own, like problems that you haven't seen before. Don't like solve problem that you already solved, at least one problem in each topic. Try to test yourself. Get the textbook, get whatever dynamics reference that you want to use, and pick a problem and see if you can translate the problem into numbers, if you can solve the problem. If you don't, there's a problem, and go revise. Okay? Because you definitely are going to see questions that you haven't seen before. It's not going to be difficult. It's going to be very close to the homework problem and the lectures problem. But the thing is going to be different problems. You need to test yourself if you can solve different problems on your own or not. Because I know many of you, I don't know if they get any help with the homework. You guys solve it in a group. You guys use ChatGPT. I don't know, whatever you want to use. So, but in the exam, you don't have any of these resources. It's just you and your brain. That's it.
Yeah, so you said there's going to be Newtonian kinematics and particle kinematics?
Particle kinetics, chapter 12.
Okay.
Like the speed, velocity, acceleration, and then the other one is the Newton's second law. And the Newton's second law, we finished the Cartesian, we finished the tangent normal, and today we're going to finish the polar coordinate system. Does anybody have any questions so far?
We're still gonna have the homework due on Tuesday as well.
Homework for is due on Tuesday. It's better that you solve it before the exam.
Okay.
So I mean, like, use it as a practice. But if you guys want to submit it on Thursday, I don't mind.
Okay.
Okay. All right. Does anybody have any other questions? Everyone's happy?
Actually, I have a question real quick.
Sure.
Are you gonna release an announcement saying like the specific things, like the specific? Because me personally, when I like to study, I like to go over like I have this thing I do that I learn something, I practice it, and then I master it. So what I do is that I have like, because usually a professor would release like a checklist or like certain topics, as well as asking you over like the Newtonian kinematics, the barcode kinetics that you asked about, and Cartesian polar and tangent coordinates that we need to know so we can solve for velocity acceleration.
It's all the stuff that we have done in the class. But I mean, if you want to put it that way, if you want to put it like in a different levels.
Yeah.
So the first level is that you have to understand the concepts. The second level that you want to master is the homework and the class level. If you want to go to the next level, you go to Hippler, or there's other textbooks. I believe I have 2 of them in the syllabus, and go big any one of these big problems that has a lot of stuff and connecting parts, and try to solve it on your own. That's, I believe, the next level if you want to master. So that's actually what I do anyway. Like before, like me when I was an undergrad student, I would finish everything in the notes, and once I'm done, I solve problems, and I make sure that I have the solutions of these problems so that I can see if what I did is right or wrong. So that's what I do, and I grade myself. I grade my I put myself in an exam. Like I don't use any resources. I don't look at any other solutions, and then once I solve it, I grade myself. I'm gonna be very harsh on grading myself and give myself, I don't know, like 70 out of 100. And then try to another time and get 80. Once you do this, thing is you put yourself in the exam environment without any resources. And once I do, that's how I did it for every exam in my undergrad, even my master's and PhD. That's how I did because there's completely different way between that you understand the subject. You might understand it very, very well, but I give you an exam and you cannot solve the exam. Either because of many things, either because of you are not good in exams. When you get in exams, you forget everything. That's completely something that we cannot do anything about it. But I believe if you practice, you are gonna get better. And so as I said, you might understand the subject very, very well, and you are very, very smart. But when I put you in an exam, you cannot connect things together. You cannot translate the problem. So first, if you have to translate the problem, and that's when you solve many exams, it's gonna teach you, oh, there is a smooth surface. Oh, that's the friction is 0. Oh, there is, I don't know, like I told you, any secret word that is gonna help you, the body is at rest. So that means that V is 0 and the V node is 0 and this displacement is 0 at time 0. So all these things that you use to solve the problem. But the thing is, that's understanding the problem. How about solving the problem? Sometimes I give you, I'm not gonna do this, like I'm not gonna give you a very, very complicated problem, but if I did, I'm not sure how, I have different scale. Maybe the problems that are not complicated to me, it can be complicated to you. But what I'm saying is there's things that you have to understand in the middle. Oh, this is, it doesn't mean that I give you a Newtonian problem from chapter 3 that you have to use maybe something from chapter 2. Oh, I need to find the acceleration. To find the acceleration, I need to use the chapter 2 equation. So this is things that you will do with practice. And once you practice more, you will find, oh, this problem is the same like the one that I solved it before. So, and also practicing, it gives you that you have like to be fast in solving the problem. Like for example, I give you a problem that is 30 minutes. If you don't practice, it's gonna take you 40 minutes. But if you practice, it's gonna take 15 minutes. So practicing is gonna help you in many different ways. Okay, is that clear? Does anybody have any questions? I'm not sure, every one of you might have different strategies in solving exams. I just was telling you what was my strategy when I was a student. It worked with me for most of the classes. There's some classes that is not easy that you can go through everything. Like there's some classes, okay, let me tell you something. Anything that has dynamics, it was the most difficult class. Engineering dynamics, fluid dynamics, structural dynamics, they are big, they are huge. I still remember the day that I was studying for my fluid dynamics final exam. I was doing the same thing, going through every concept in fluid dynamics. And I wasn't able to finish it all, and I didn't solve any problems. And I went in the exam, even that I have everything, I understand everything, but I didn't practice. I understand everything in the notes, but it's a very huge subject, but I need to practice to solve the exams, and I didn't do that. I didn't get the grade that I want, okay? Right, so yeah, I mean, it's gonna be 4 questions. We only have 2 chapters. It's not like a final exam, so it's manageable. If you study over the weekend, you can, I believe, do it, okay? All right, so let's finish at chapter 13.
Yeah.
Chapter 13.6, I guess, yeah. So this is one is Newtonian particle kinetics using polar coordinate system, RMA. So as you guys remember when we were talking about the polar coordinate system in chapter 12, we have like, this is the Cartesian coordinate system, X and Y. And let's say that our particle is moving on this curve, something like this. The position of the particle from the origin can be described by a vector r. This is the r vector, and this is our particle. Do you guys remember how we can map the r theta axis? Where's the direction of the r axis? It's always in the direction of the r, something like this, right? So r is that way, is always in the positive r direction. That's r hat. How about theta? I told you that theta is increasing that way. So where's the theta axis? It's perpendicular to the r in the direction of increasing theta, right? Right, that's r theta. Do you guys know how to map the tangent normal? Tangent is always tangent to the curve. That was the tangent direction. And the normal is perpendicular to the tangent in the direction of the radius. That's the n hat direction. So that's the 2 axes together. Do you guys remember this curve from chapter 12? Okay. All right. So I have this here. So Newton's second law, as you guys know, it is always the summation of the forces on any body is equal to the mass multiplied by the acceleration. And it's a vector quantity that has a direction, so that's why I put vector and F and vector and A. There's no vector in the mass because mass is a scalar quantity. Doesn't have direction. Okay, so if this is a Cartesian coordinate system, we can divide this into two components, x and y. If it's tangent normal, we can divide it into F tangent and F normal. But if it's r and theta, same thing. We can say the summation of the forces in the r direction equal to MAR, and the summation of the forces in the theta direction equal to MA theta. That's the two components of the forces. And that's when I told you in a little bit that sometimes we can use equations from a chapter 2. So if you want to find what is the value of AR, you can go to the equation sheet and find what is the value of AR. It was like, it has a lot of R dot, theta double dot, same thing with A theta. Okay, so right now we know how to get the acceleration, and we call this the radial acceleration, and this is the radial acceleration, and this is the angular acceleration. Okay, the theta one. That's very easy. I can give them. So basically, in the problems, I will give you that r is equal to something function in theta. So first you have r, and then you can get r dot by differentiating with respect to time, and then r double dot. And theta dot, and theta double dot is going to be given in the problem, or I can give you a way to get them. So basically, you will be able to get the acceleration AR and A theta. There is a way that you are going to get them. The thing is all the forces. How can I get the forces? That's why you need to understand the different types of forces. Sometimes the force can be the weight of the body. We have the weight. What other forces that can be on a body? We dealt with weight, right? It's always in the g direction. What else? Forces. The normal force. What is the normal force? It's force from the surface to the body. It's always perpendicular on the surface. And by the way, it's always in the direction of the n hat direction. But it can be positive direction of n hat and negative direction of n hat, because that's a very, very important thing to characterize the forces on a body. Like, let's say my body's here, and that's my surface. It's a curve. The normal force is that way, right? The body weight going down. The thing is, n hat is that way, right? Always in the direction of the radius. But if my body is here, and it's like, that is the normal force from the surface on the body. That's how you should do it. So sometimes it is the n hat direction or the negative n hat direction, but it's always positive or negative n hat. So that's the normal force. What other forces that we have? The friction, right? So what is the direction of the friction? Like, if this body is moving that way, it's always tangent to the surface. Like, if your surface that way, so the friction is tangent to the surface. If your surface that way, it's still tangent to the surface, okay? So, and is it in the tangent direction or in the negative tangent direction? Like, let's say my body is going that way. That's the tangent direction. It's always in the negative direction of the tangent. That's basics that you should know. How to map the forces on a body. Like, let's say this body is moving that way. Okay, that's the tangent direction. I know that there's a friction that way. And I know that there is weight going down. And if there is a pushing force, this pushing force P is going to be that way. So when I give you a problem, I'm not going to put these forces for you. You have to understand the problem and try to map these forces. Like I told you, if there's a car is moving on a curve, this car is moving that way, so, and then the weight is going down, and there's a friction, and there's the normal force. You have to map all these forces by yourself. And there's another important rule. When you have any curve, put this in front of your eyes. The normal acceleration always equal v squared over root. The velocity square over root. That's something that you shouldn't forget. All right, so all this stuff we have done it before. What is new when it comes to r and theta? So the thing is, usually r and theta, like usually the problems that include r and theta, it's always have an arm, like a mechanism. Oh, I forgot to print the problem. I printed it, but I forgot to bring it. Okay. That's the problem. Let's write it down here. So let's say that we have like not the circular pass, it's like a pass like that has that shape, and it's fixed here, and fixed here. And here I have like in the middle, and the thing is, this arm, this is not a circle. Like the radius here is not constant. It's like a part of an ellipse or something. And the radius r here is variable, and r is equal to 1.5 2 minus cosine theta. By the way, this is the radius r, and let me put theta something like this. Say r is like in the center. This is r. Keep it square. And this is the angle theta. The thing is, for this bar is connected to this ring, but to be connected on this ring, there is a way, like there's a collar here, like two of them. One of them that allow this bar, the r to be increased and decreased on the length, because r sometimes here is small, here is big. So there is a way that this arm cannot be attached to this ring. I mean, like it's attached to it, but it can move between them. I don't have the drawing, but I have a similar one. Like look, but it's a different one, like different problem. Can you see this ring? And it has an arm, and this arm has something connected to that allow the arm to move on the ring while being attached to the ring. Okay. All right, but the thing is, this arm, when it moves, like to move it, there's a force that pushes this arm. Like let's say that you put your hand on this arm to push this arm to move on the ring. Usually the arm force is usually in the direction of the theta. Like let's say this R is my arm, and you move this arm in that way, you need to push that way perpendicular to the R, which is in the direction of the theta direction. So if you have an arm in a problem, I told you find the arm force. The arm force is always something in the direction of the theta direction, in the increasing theta. So if you are pushing down, so that means that the direction of increasing theta is down, so that the force on the arm B is in that way. Alright, so yeah, before I solve this problem, I want to tell you, yeah, we talked about the normal force. The normal force is always from the surface in the m direction, the friction force, and the weight of the particle. The weight of the particle is always going down. We talked about the weight, so we mapped all these forces. So yeah, the last thing that I want to talk about before I leave this to solving a problem is a new angle. It's called the angle between the R and T. It's called XE. This angle. So it is in between the R vector and the tangent vector. By the way, this is very, very important angle, and definitely in the second midterm there's a question on it. Okay, try to understand this correctly. That's a 10% question. Okay, what is the angle XC? The angle XC is the angle between the R vector and the tangent vector, and it's always acute angle, not obtuse angle. So that means that XC is more than negative 90 degrees and less than 90 degrees. And how can I find it? Basically, you map the R theta vectors and the tangent normal vectors, and once you map them, try to find the angle between these. Sometimes you will find that the R vector is going that way, and you will find that, for example, let's say this is R and theta, and you will find that the tangent is that vector and the normal is that big, okay? So you will be like, oh, R and T is something like this. So this is the angle, but this angle is like 120 degrees. It doesn't work that way. How we do it, we get the negative R hat, and this is the angle XC. Okay? Right now, my XC is positive. Like right now, I just got it. For this specific problem, it's positive. Other problems, you will find R and T that way, and you are gonna get an angle more than 90 degrees. The thing is, you have to step R to the negative direction and get the angle XC. Why? Because we have a rule to calculate this XC. We say that the angle XC is equal to the tan inverse of R over the dr d theta. And this one is always gonna give you an acute angle less than 90 degrees, okay? All right, you will tell me, how can I get this? Basically, I'm gonna give you R, in the problem, like something like this, and then you differentiate this with respect to theta, and you put it here. But for our problems right now, R is function in theta, and if you get the R d theta, it's still is gonna be function in theta. So definitely I'm gonna ask you at a specific theta. Like let's say at theta equal 120 degrees, find something. So you will get XC when theta is equal 120 degrees. Okay? Alright, so let's see what we have in this problem. You have an arm that is pushing on this ring, and the R is changing in this using this function. And I give you, for this problem, I want you to find at theta equal 120 degrees, and I give you that the angular velocity theta dot is equal to 5 radian per second, and it's constant. Since that's also one of the stuff that you can get in the exam, and you have to, if I give you that the radial velocity is constant and it's 5 radian per second, you will tell me what is the theta dot. 0, right? I'm not gonna tell you that. If I told you that the velocity is constant, that means the acceleration is constant. If the radial velocity is constant, so the radial acceleration is 0, okay? All right, so I give you all the thetas and I give you R, and I told you that the weight of the color here, like there's a connection between them that allow this part to move. I give you this weight is equal to 0.75 pounds. And I ask you to find what is the normal force that the surface acting on this body. I want to find what is the normal force here and what is the pushing force of the arm. Like if you push this arm, what is the value of the weight? Like if you have a weight here, this weight is gonna make this part move down. I want you to find out what is the force being used on this arm by this weight, and what is the normal force from the surface on the arm. The thing is, as I told you, to solve any problem like this, you have to draw a free body diagram and you get points for that. If you didn't, you're gonna lose points. But to do this, before I take this body out and map the forces, I want you to find out with me what is the tangent normal and what is the R and theta. Okay, R and theta is very easy to do it. I'm gonna use the same colors that I used here. Let's find R and theta. I'm gonna use purple. So R is going that way, so R is always in the direction of the arm. That is R hat. How about theta direction? Theta direction is always perpendicular to the R. Like if R is that way, so that is the theta, in the direction of increasing theta. That's the theta hat. And the angle between them is 90 degrees. How about tangent and normal? Look at the tangent. The tangent always tangent to the curve in the direction of the increasing velocity. So that is the tangent. That is T hat. And the normal is always something like this, perpendicular to the tangent, going to the center of the curve. All right? Okay, so we mapped both of them. You guys tell me, where's the angle XC in this one? Green? And R, right? So that's the angle XC. So is that one is the right? Is that one less than 90 degrees? Or more than 90 degrees? From what I see here, it's less. Why? Because this and this make 90 degree, and it's a little bit less than 90 degree, maybe 70, 80 degrees, but it's still less than 90 degrees. So that's the angle XC. All right, we are gonna find angle XC in a little bit, but right now we mapped the axes. Let's draw the free body diagram. That's the body that I'm looking at. That's the body that's moving. That has the weight. I neglect the arm weight and I neglect everything. So that's the body that has the weight. If I take this body out, and by the way, this is a horizontal curve, not a vertical curve. Like in the real life, this is not like this. This is something like this, and the arm is moving that way in the horizontal direction. That's a very, very important piece of information. Okay? Why? Because right now you are going to have r and theta and z, and the weight is in the z direction. If you have a vertical curve, this is r and theta, the weight is going down, is going to have a component in the r and theta direction. Okay? But if this is moving in the xy direction, so weight is going down, it's completely different. We're going to see it right now. So that's a horizontal curve, and that's the body that I'm looking at. It has 0.75 bound. If you don't understand the problem, like let's say that the problem you cannot translate it very well. You don't know what are you dealing with. Am I dealing with this weight? Am I dealing with this bar? Whatever I give you mass for, that's the body that I'm dealing with. Like if I give you a mass of the bar, that means that this bar is the one that you are dealing with. If I give you the mass of the color here, that's the body that I'm dealing with. Okay, so the thing is that I'm giving you mass for, take it out and put it and draw the free body diagram for it. Okay, don't put something that I didn't give you a mass for. All right, so this is the bar that I give you a mass for, and it's equal to 0.75 pounds. And let's map the r and theta. So I have r had that way, and I have theta had that way. Let's put the tangent and normal. So I have he had that way, and this one, and had that way. Alright, I'm gonna extend this. We agreed that the angle at C is this angle. Alright? Okay. This angle and XC is equal to, you guys know? XC and this angle is 90 degrees, right? Because this, the tangent and normal are perpendicular to each other, so the extension also is perpendicular. Okay, and also this angle and this angle are 90 degrees, right? Because they still the verbal polygon. If this and this are equal to 90 and this are equal to 90, so what is this angle? This is XC. XC and this angle is equal to 90, and XC and this angle is equal to 90. That's geometry, okay? All right, so, and we can say also that this angle is equal to XC, right? They are opposite to each other, right? Something like this. So this and this equal to XC, this and this are equal to XC. I'm just trying to map the angles. I didn't do anything. If you go and put these together, you are gonna find that they are equal to each other. Okay, so that's right now I'm trying to find the angle. Let's map the forces. What forces that we have here? First, you are gonna tell me the weight, but I told you that's really good guess. But I told you this is a horizontal curve. Okay, so what I'm trying to do, I'm trying to see the movement in the vertical direction. You can put the weight, but don't mix it with the vertical direction. Like if this a vertical bar that is moving that way, yeah, I would put the weight. Okay, But I didn't put the weight because that's a horizontal curve, and I'm gonna tell you the weight is not gonna help me, but the weight is one of the forces that are there, okay? All right, so this curve, I put it vertical on the board because there's no way that I can draw it horizontal, okay? Unless that I can make the board as horizontal, so I have to make it that way. So it's horizontal, and then I put it that way. All right, let's map other forces. I have the pushing, that's actually what is asking me in the problem. Find the B, the pushing, the arm, the pushing force of the arm, and find the normal force from the ring on the arm. Okay, I told you, if you have an arm that is moving that way, there is always a force that is pushing this arm that way. Like if this arm is moving, that means that always the force of the arm is perpendicular to the arm. So this arm is moving down, so it's always in the theta direction. So I have, this is theta, so I look for theta and then I put B in the direction of the theta direction, B. How did I do that? Right, this is your arm, it's going that way. The perpendicular is the one in the theta direction. So this arm is moving, there is always a pushing force from the arm in the theta direction. Okay, that's B. How about the normal force from the surface? We said that the normal force from the surface is always in the direction of the n hat direction. So look at the n hat, that's the n hat, and the force is always perpendicular to the n hat. Like if here, that's the tangent and that's n hat. So that's the normal force from the surface. If here, that's the n hat direction and that is the tangent, so the surface has a normal force that way. It's always in the n hat. So that is the n hat. So I'm gonna have the normal force is in the n hat direction. Let me just focus. I found it's positive or negative. So if this body is down, the n hat is gonna go that way, but my body's up at 120 degrees. So the normal force of this surface on this is going that way. So I have a normal force in the direction of the n hat, something like this. That's the only two forces that I have. I mean, I have in the horizontal direction, like I told you, this is a horizontal ring, and the forces is going that way. The weight is going down, okay? Weight is going down, but these forces pushing, like the arm is pushing that way, so the force is in this surface. The normal force in this direction. If you told me, oh, I have a weight, and I need to put the weight something like this, that means you take the weight and you make the weight in that direction, not going down. Okay? Alright, so alright, so right now I have B and I have the normal forces. I put B and N, and what I'm trying to do, I wanna solve this equation, summation of the forces in the R and in the theta direction. But to do this, before I do it, I need to find what is the value of AR and what is the value of A theta. And I told you that's supposed to be the easiest part. How? I'm gonna give you all the information about R and all the information about thetas, and you have to do kinematics from chapter 12 to do that. So, first I have R at theta equal 120 degrees, gonna be equal to 1.5 2 minus cosine 120 degrees. And this is gonna give me 3.75 foot. And I need to get R dot. R dot, you guys tell me, how can I get R dot? I have to differentiate with respect to the time. Can you differentiate this with respect to the time? Tell me. I'm gonna write. Can you differentiate 1.5 parentheses 2 minus cosine theta? It's gonna be 1.5. What is the derivative of 2 with respect to the time? 0. What is the derivative of negative cosine theta with respect to the time? It's gonna be negative minus what? What is the derivative of a cosine? Is sine or negative sine? Negative sine. So I'm gonna put negative sine. So you guys, when you said sine theta, you did minus
yeah.
Amazing. Okay. Right. This is gonna be sine. What else? I wanna say amazing again. That's it. Should I close and I'm done? d dt of cosine theta. Remember, t is not theta. If I said d theta, you're right, negative sine theta. And that's it, d theta, and that's 1. d dt is going to be equal to negative sine theta multiplied by d theta dt at the end, which is negative sine theta dot. Are we all agree on this? Okay, so I'm gonna have here at the end theta dot, so that means that we have 1.5 sine theta dot. I told you that's really, really important. You should know this as a basic differentiation. Okay? Right. What is coming next is much more difficult. R double dot. By the way, when you substitute with theta equal 120 degree and theta dot is equal to 5, this value is gonna be equal to 6.45 feet per second squared. Feet per second squared. I already have theta, 120, I already have theta dot is 5. Can you guys tell me what is the derivative of R double dot? I want to differentiate this, right, with respect to the t. Can we do it? How can I do it? You have two variables. You have theta, sine theta, and you have theta dot. But actually, if I want to make it easy for myself, easier than here, I know that theta dot is constant, it's not a variable. And I can put this 5 right away, and it's going to be right. But what I did here in the notes, I assumed that theta dot is variable, and I'm gonna deal with it as theta dot. I'm gonna keep it. Like, let's say I give you in a question that theta is not variable. Theta dot, sorry, it's not constant. It's a variable. So that means that you have two variables, this function and this function. You remember, if you have g equal to x and y are like two variables, and you want to get dg dt. The derivative of the first multiplied by the second, the derivative of the second multiplied. There's the same thing here. So this is going to be the derivative of the first part. I'm going to deal with it, this one as a one function. So this is going to be equal to 1.5 cosine theta multiplied by theta dot. That's the first one. Multiplied by another theta dot, this one. This part is the derivative of this part. 1.5 is going to be cosine theta, d theta dt, which is this part, multiplied by the theta dot out there, plus the first function, 1.5 sine theta multiplied by the derivative of this with respect to the time is going to give you theta double dot, right? Okay, so I'm going to have this is going to be equal to 1.5 cosine theta dot squared plus 1.5 sine theta double dot. When you substitute here, theta double dot is equal to 0. That's why when I told you, if you substitute with this part as a constant, this part is definitely going to be 0. And I can find this part is going to be equal to negative 18.75 feet per second squared. Okay, does anybody have any questions so far on what I did? All this is basic differentiation. I give you R, function in theta. I asked you to find the first derivative and the second derivative. That's a basic math. I didn't do any dynamics yet. So the dynamics is coming after when I try to find AR and A theta. You go back to your equations.
Sorry, so for theta dot, you gave it to us in radians per second, but you're writing it in feet per second. So
Okay, so this is R. R is always, okay, that's a good question. All right, let's say, when I say that theta is equal to sine 100, theta is equal to 120 degrees. In your calculator, when you calculate the sine, you have to make sure it's radian. It's a degree, so you put 120 in degrees. Okay, that's something that you have to deal with, to know what is the difference between the radian and the degrees. Now, when I put theta dot here, if it's outside the sign, it should be radian. like this is always gonna be radian, so I put it as a 5 radian per second. But the thing is, R's are not angles. R are like, it's like still linear distance, but it's on the curve. So this is R, that means like, let's say this is 5 feet. If you cut this 5 feet in 2 seconds, that means that R dot is 5 over 2 feet per second. So it's always feet per second. The only thing that is angle is theta, right? Like it's degree. And maybe I can give it you as radian, like I can give you 120 over 180, and finally this is it's gonna be 2 over 3, 5, and I can give it you in radian. Okay? But make sure that you have all the units are consistent. All are radian or all are degrees.
So when you're getting the answer, you're also plugging in theta dot that was given to get the 5.45
Yeah.
feet per second. So you don't include the radians that's from the theta dot?
I include this as a radian.
Right.
Yeah.
But not in the final answer when you say negative 18.75.
This one,
Yeah.
I put it here as a 5.
Okay.
5 is squared. And when it with
Oh,
theta,
but
I
you
can
don't
put
put the
120 degree. No, I don't put the, unless there is the units are changing, like the one in the homework, I give you something in mile per hour
Right.
and something in feet, so you have to make all the units are consistent. All right, okay, sure. Okay, so right now I'm ready to calculate AR and theta. If you go back to your equations, you'll find that AR is equal to R double dot minus R theta dot squared. That's back in the kinematics. And A theta is equal to R theta double dot minus plus 2R dot theta dot. So basically I have all the R dot double dots, I have all the theta dot double dots, so you basically substitute here, and you are gonna get that AR is equal to negative 112.5 feet per second squared, and you are gonna get A theta is 64.5. That's a good question. I think that is gonna get back to your question that you asked in a few bit, like in a little bit. I have here AR as a feet per second squared. A theta should be radian per second squared. I have it here as a feet per second squared. So this should be radian per second squared. So you have to change the notes if you guys, because I really have it as feet per second squared. Okay, so I have AR and A theta. So right now I can substitute in the Newton's second law the sum of the forces in the R and sum of the forces in the theta. So let's put them here. Sum of the forces in the R direction is going to be equal MAR. You guys tell me, what forces here that are in the R direction? I have B and I have M. Which one is in R and which one is in the theta direction? I know that B for sure is in the theta direction. There is no component of the B in the R direction. I told you, if you have an arm that is moving, this is the R direction and the force is always perpendicular to the R, pushing to the arm like this. It has no components in the R direction. All the component is in the theta direction. So for sure, B is not in R direction. But the normal force has a component in the, because it's in the n hat direction, I can find what is the component in the R and what is the component in the theta direction. So you know XC, if you know XC, you can find out here is gonna be n cosine XC, and here is gonna be n sine XC. So you guys tell me what the component should I write here. This one is in the negative R hat direction, so I have negative n sine XC alone is in the R direction. And then I multiply by the mass, I already give you the weight is 0.75, so I can put here 0.75 over 32 0.2 because I need to convert from weight to mass, multiplied by AR, which is negative 112.5. All right, here I don't know what is the normal force and I don't know what is the exceedance, but I give you this one that you have to memorize. I'm not sure if it's in the equation sheet or not. So I can find what is the value of XC. If I know what is the value of R, I want to find what is the value of XC and theta equal to 120 degrees. So basically, I know R at 120 degrees equals 3.75. If I want to find dr d theta, so I need to differentiate this with respect to theta. By the way, you will tell me we did this, we got R dot by differentiating dr, but we differentiated dr dt, not dr d theta. Okay, so let me put that here, dr d theta. If you know that this is R, 1.5 multiplied by 2 minus cosine theta, and I want to differentiate it with respect to theta, that's much more easier. So it's going to be equal to 1.5 multiplied by, the 2 is going to be 0, minus sine theta, d theta, right? Because I'm differentiating with the theta, so this is 1. So it's going to be equal to 1.5 sine theta. So we don't have the theta dot that we have here, because we differentiate with respect to the theta, not with respect to t. Okay, do you guys got that? If you didn't get it, I'm gonna put it here. R is equal to 2 multiplied by, because, oh sorry, 1.5. 2 minus sine theta. So earlier I got R dot. Right now I want to find dr d theta. Earlier R dot was dr dt. That's completely different differentiation. You guys understand that? We want to try to find what is the time rate of the change of R with respect to the time. Right now we try to find the rate of the change with respect to theta. That's completely different quantities. So if I want to find out that, I have to differentiate this. 1.5 is outside, so I'm going to differentiate, it's constant, so I'm going to keep it outside. I'm going to differentiate what is inside. 2 is 0, and this one is negative, and this one is going to be negative cosine theta. And I told you, after you differentiate any function, at the end you have to put dt, the one that you have here, with the variable that you differentiated to. I differentiated d theta with respect to dt. Same thing I will do here. It's gonna be equal 1.5, 0, because the time rate of change of 2 of a constant is 0, minus, and then I'm gonna have another minus, cosine theta multiplied by d theta, same thing that I have here. Look at this, and look at this. I put this here at the end, and I put this here at the end. And then I'm gonna put the variable that I'm differentiating is d theta. Alright? I'm gonna close the parentheses. Definitely this is negative, negative is gonna be positive, as you guys did it in a little bit. Alright, what I have here, d theta, what is the time rate of the change of theta with respect to itself is 1. Okay? So that's equal to 1. But what is the time rate of the change of theta with respect to the time? That's a theta dot. Okay? So that is the difference between the two. Alright, so this one is going to be equal to 1.5 cosine theta, and this one is going to be equal to 1.5 cosine theta dot. Alright, so if I want to find the XC, it's going to be equal to tan inverse R over dr d theta. So R is equal to, I already have it, 1.5 2 minus sine theta. and drd theta is equal to 1.5 cosine theta. That's the general function, but if you want to find it at theta equal 120 degrees, that is going to give you theta is equal to 70.88 degrees. Does anybody have any questions on this? All right, you have to understand XC very well because there's definitely a question about it, and I believe either this midterm or the next midterm, actually this midterm. XC, because you already got it right now. So understanding XC, what is XC, how to calculate it, like the way that I did it here, don't mix between drd theta and drdt, and you have to know if it's the angle between R and T, so you have to be able to map it. Okay. All right, so I give you XC. Right now I know what is XC is, so I can say that the negative normal force is equal to sine 70 degree 0.88 is equal to 0.75 over 32.2 multiplied by negative 112.5. And from this you can get what is the normal force equal to. The normal force is going to be equal to 2.77 pounds. Right? The second equation, the second Newton equation, is the one in the theta direction. Sum of the F theta is equal to ma theta. All right, that's fine. What is the forces in the theta direction? I told you always the arm is pushing in the theta direction, so I have B is positive. And I have a component from the normal force, it's n cosine theta. So this is a positive n cosine theta, so I put all the forces. Then I have the mass 0.75 over 32.2 multiplied by a theta, which is the one that I calculated here, 64.5. And I know n, I know theta. Oh, by the way, this is not theta, this is XC. Because here's the angle was XC, and I was getting the sine and the cosine of XC. And I know XC, I know N, and then B is going to be equal to 0.6 pounds. All right, we spent 1 hour solving this problem. But the thing is, I was explaining everything in this problem. In the exam, you are going to do all this step by step. Let's see what we did. All what we want to do is to solve these two equations. Just be systematic. I only have this equation and this equation to solve. All right? So I want to find what is the value of AR, what is the value of A theta. Okay? Take it step by step. I try to find what is the values of theta, theta dot, and theta double dot. I got them 120, 5 radian per second, and it's constant velocity, so this is 0. I didn't do any equations or I didn't solve anything. All this from understanding what is given in the text. I didn't solve anything, I didn't differentiate anything. The next level, I give you R as a function of theta. So if you want to find R dot and R double dot, you have to do some differentiation and be careful with what variables are you differentiating to. Are you differentiating with respect to the time or with respect to theta? Things that we have done over there. So I know that R dot, when you get velocity, you are differentiating with respect to the time. If you get acceleration, you're differentiating with respect to the time. So I get R dot, R double dot. I'm done. So I was able to get AR and A theta from the kinematics equation. I don't memorize these. I have them in the equation sheet and I put them and I found what is the value of them. So, and the mass, I give you the weight. The weight is 0.75 pound. I divide the weight by G and make sure about that you have your units right. This is pound, so you divide by 32.2, which is feet per second square acceleration. But if this is kilograms, you divide by 9.81. Okay? So you got the right-hand side of both equations. Okay? I'm done with this. Let's find the left-hand side. For the left-hand side, you have to draw the free body diagram. And also you have to draw the, maybe if you didn't, I can let it go, but I want to know that you understand what is the kinetic diagram is. Like, I know that this body is this way. I know that R has in this direction, and theta has in this direction, and this is the direction of M, A theta, and this is, let's assume this is the direction of M, A R. That is the direction of my acceleration. Okay? All right, that's what we call the kinetic diagram. But that's the most important part, the free body diagram. What I did in the free body diagram, I mapped the r theta, I mapped the tangent normal, and I put the forces on this body. Like I put what forces? If there's an arm that is pushing, I told you that I'm not gonna tell you where speed is. If there is arm and this arm is pushing on a ring, the B is always in the theta direction. And the normal force is always in the n hat direction. And we talked about if we have a curve like this is the normal force. If we have a curve like this is the normal force. It depends how's your body is locating. Like let's say that you are biking or your car is moving on. So always the surface having a normal force like this on you. But let's say that you have a ball here and this ball is moving here, so the normal force is coming from that way. So, and it's always in the n hat direction. That's the n hat direction. Okay, so that's what we did, and we did some angle analysis to find the sine theta and cosine theta to solve the problem. So yeah, this is one of the most difficult problems because you have to do a lot of things. You have to do dynamics, you have to do math. But if you think systematically and do this step by step, 1, 2, and take every one alone and deal with it, it's gonna be not that difficult. Okay? Does anybody have any questions so far?
I think the units you had in the notes were the correct one.
Which one? For what? For what? This one?
Yeah.
I put it radian?
No, if you had feet correct, that would be angular acceleration.
This is the angular acceleration. Sorry, this is the radial, this is the angular. The radial is feet per second squared. The angular
But
is
wouldn't the
radial.
angular be on alpha meters?
Yeah, this is like alpha.
But that one is not measuring.
Anything that is radial is gonna be radian. Like even when I give you the velocity, I didn't give you the velocity 5 feet per second. It's 5 radian per second. Because it's how much radian you cut per second. Okay? Alright, so right now we are done with chapter 13. I'm gonna give you, does anybody have any other questions? Okay, we are done with chapter 13. The exam is gonna be until to this point. So you have to understand everything until to this point. Anything that I'm gonna explain right now is not in the exam, but it's in the midterm too. So you have to understand this concept for the next midterm. So right now I'm gonna give you a little bit of introduction about the work and energy principles. Right now we are done with forces. All right. Chapter 14, work and energy. All right. So let's talk about work and energy. All what we have done before, it's just all about force. Like let's say I push this body with a force that way. My force is like 5 Newton, and this body starts moving. Okay, so all this is force. What we are going to talk about now is what is the work that this force did on this body. So, work, we define it as the amount of energy transferred to a particle to change its position. So, if you have your bodies here and you keep pushing this body and you put some energy, is the amount of energy that you put in this body to change its position. And it's usually always understand it like this. Work is force by displacement. So let's say that you put a force 10 Newton and this body moved 5 meter. So you put 10 multiplied by 5, that's 50 Newton meter. Okay? So, and always make sure, like let's say here I'm saying that a force F will do a work on a particle if the particle undergoes a displacement in the same direction of the force. Okay, let me tell you, if you put a force on this body that way, and somehow this body moved that way from other forces, like let's say this body has a lot of forces, like has a motor, and this motor is moving that way, and you put a weight on this body on the top. This weight is making a force on your body. It doesn't make any work. Like let's say that there's a force that way and your body's moving that way. This force is not making a work for this body to move that way. It needs to be that the force in the same direction of the movement. And there is no way that like your body's moving that way and the sum of the forces are all in the other direction. So like it's intuitive that if you have a bunch of forces acting on this body, the body's gonna move that way, so that means like the sum of the forces multiplied by the displacement. But the thing is, what if you have a force that has an angle? Like you push the force, I push this that way. Exactly, so I have to find what is the x component, y component. Which one that is making the work? Is the one in the y or the one in the x direction? The one in the x direction. The one in the y direction doesn't do anything. So it's always the one in the same direction of the motion. So that's why if you want to find the work acting on a body, and we always say it's u, it's always the F vector multiplied dot product with the R vector. Okay? What does that mean? You guys know what is the dot product is? Like if you have A vector, we did this before I guess, B vector, and there's an angle theta between them. So A multiplied by B, and both are vector, and we do dot product. You tell me, the quantity that comes from dot product, is it a scalar or vector? Scalar. And this is equal to the magnitude of A multiplied by the magnitude of B multiplied by the cosine theta between them. Okay? That means basically, you find what is the component of A in the B direction and multiply it with B. Like this, like A has a component here is equal to A sine theta, and a component here is A cosine theta. And that means this part and this part. So you take the one and the same component. Same thing with this one. If your force, let's say that you have a body like this, and this body, you put a force F that way. It has an angle theta. And this body start moving that way from point 1 to point 2, and this is the R direction. The one that made the work is the one in the cosine theta direction. And basically, if you try to find out the result from this multiplication, that's equal to F vector multiplied by the magnitude of the R multiplied by cosine theta. Or you basically, I'm gonna find the component in the direction of the movement, and this component is the F cosine theta, so I multiply F cosine theta by the distance S, right now I got the work. So there's different way to do it. But let's put the general rule of calculating the work. It's the same thing like I have done here, but let's say that we have a curve like this, and this is the origin, for example, and this is the position number 1. This is the R vector, and this is the final position R2. And your body is here, and there's a force acting on this body. F vector. And if we got a dr, this is the angle between them. This is dr, this is the angle theta. And definitely theta isn't changing, like let's say this is d theta. So we say the infinitesimal work exerted, like du, is equal to the force that you have multiplied by the dr vector. And if you want to find the magnitude is going to be the magnitude of the F multiplied the magnitude of the R multiplied by the cosine theta between the two vector, and the magnitude of dr is the ds, is the distance travel, like from here to here. So this is basically F vector multiplied by ds equal, and let's remove the vectors. It's gonna be F multiplied by ds multiplied by cosine theta. If we wanna find just the amount of work done at this part. Why this part? Because at the dr, like if you take a little bit here, dr is equal to ds. Because that's a really, really infinite part. But I can take a big bar and say that the dr between here and here is equal to ds. No, there's a big difference. That's dr and that's s. Let's say this is r and s. But if we take a small piece, the differentiation between the start and the end is not that big. So dr is equal to ds, so we have it something like this, but this is du. If you want to find u, like we always use the word as a w or u, but here I'm going to use u. So we say that u from point 1 to point 2, like for body to go from point 1 and end at point 2, you have to integrate the forcing function multiplied by ds cosine theta from point 1 to point 2. And this can be written as like you have to integrate this. Actually, you can write it like I can. Let me write it that way. I'm gonna write it like as an f vector multiplied dot product multiplied by r from location 1 to location 2. That is this one here. Okay. Same thing if I did this from S1 to S2, and this is gonna be f ds cosine theta, which is this part. So it's either this part or this part. Both of them are the same. So basically, the integration of f cosine theta ds from S1 to S2 is gonna give you the work from 1 to 2. All right. The thing is why I put it as an integration. I put it here as f cosine theta by s, and I told you this is the work. That's right. Okay? But this is assuming that the force is constant. But what if I told you that the force is increasing, or the force have a function or something? The thing is you have to do integration. You have to keep the force under the integration. If there is nothing that is variable, like f is not variable, you can take f out of the integration. And then you are going to end up with something like this. All right? So, all I want you to remember that the work from point 1 to point 2 is the integration from S1 to S2 of the force cosine theta. As theta is equal to 0, so cosine is going to be equal to 1. That means that all the force in the same direction of r, and this is ds. And by the way, we always can put the integration form in a curve form. Like let's say if I want to find the graph that describes the relation of s with the force f, and let's put f cosine theta. Now let's find that we have like something like this. This is S1, and this is S2, position 1, and this is position 2. And this is the forces exerted at each one. If you find the area under this curve, it's going to give you this integration. This is the integration of f cosine theta ds. We all know that any integration, the integration of a variable x, d, s or something, if you draw x on the y-axis and s on the x-axis and you draw the relationship between them, if you find the area under this curve, it's going to give you the integration. Integration means the area under the curve. It basically means if you take a strip here, you guys remember when you were doing integration and take a strip and you integrate this strip? This strip has a base, like if you take this strip out, it's going to be something like this. It has a width of ds, and it has a height here. This one, we can say it's like something like this. This height of the strip from here to here is f cosine theta. Alright? If you take the area of this, d as cosine theta, and you integrate this strip from S1 to S2, you will get the area under this strip. That is the definition of the integration. Okay? Alright, so I'm gonna stop here right now. All what I want to do for next lecture that you all know that the work from any point 1 to 2 is the integration of f cosine theta dx. And then we're gonna take it from there next time. Alright? Does anybody have any questions? Alright, see you guys next time. Can somebody bring me the phone because I forget it last time?